Yeah, this is ELC131, Circuit Analysis 1, and this video is on Norton's theorem. Now, Norton's theorem states that any linear electrical network consisting of voltage sources, current sources, and resistances can be replaced with an equivalent circuit consisting of a current source and a parallel resistance as shown in Figure 1. Now, the steps to take in deriving the Norton equivalent circuit are: 1. To find the Norton current, IN. This is the current through the terminals A and B with the terminals A and B short-circuited. Step 2 is to find the Norton equivalent resistance, RN. This is the resistance between the terminals A and B, with all voltage sources replaced by a short circuit and all current sources replaced by an open circuit. Step 3, connect IN and RN in parallel with the terminals A and B. This is the Norton equivalent circuit as seen in Figure 1. Then replace the component or components that were originally connected to the terminals A and B. In this video, we'll look at an application of using Norton's theorem to analyze a series parallel circuit with a single resistance connected between terminals A and B. But understand that connected to these two terminals can be a circuit, many components, a circuit, another circuit, or even a sub-circuit. Again, this gives us a way of reducing a very complex circuit to a more manageable or an easier to analyze circuit. So let's look at a circuit example for the Norton theorem. So we see a series parallel circuit in Figure 2. And we're going to derive the Norton equivalent circuit for the terminals A and B in that circuit. And we also state this as saying that we will find the Norton equivalent circuit as seen by RL. Then we're going to use the Norton equivalent circuit to find the current through RL. So step 1, we find the short circuit current through the terminals A and B. Now, when I place a short from the terminals A and B, the resistor R2 is shorted. So no current will flow through R2. All the current that flows through R1 will flow through the short circuit. So the current from terminals A to B, the Norton current, is equal to the current that flows through resistor R1, which equals V source divided by R1, 5.45 milliamps. Step 2, we find the resistance between terminals A and B with V source replaced with a short circuit. And this is the same procedure we use to find the Thevenin equivalent resistance. Note, with V source shorted from terminal A to terminal B, I've got two paths that I can take to get from A to B. One is through resistor R1 and one is through resistor R2. So the resistance from A to B, the Norton resistance, equals R1 in parallel with R2. Again, we can calculate this using the product over sum. Gives us a value for the Norton resistance of 1.1 k-ohm. So then we place IN and RN in parallel with the terminals A and B. and connect the component or components that were originally connected to those terminals. So the circuit of figure 5 shows us the Norton equivalent circuit of the circuit of figure 2 with respect to terminals A and B, or as seen by RL. Now we can calculate the current through resistor RL by using the current divider formula. So IRL equals I Norton times R total over RL. Again, this is our current divider formula. So IRL equals 540 microamps. Now, generally speaking, we use the Norton equivalent circuit when we're concerned about the current that's going to flow through some component or group of components connected between terminals A and B. And we'll use the Thevenin equivalent circuit when we're concerned about the voltage across a component or components connected across terminals A and B.